The project begins with a careful selection of sprockets and chains from a mechanical scrapyard. The engineer selects a suitable pair of sprockets and a roller chain. To set up the primary drive system, 2 sprockets are placed on a flat surface to test fit the chain, to evaluate the engagement and gear ratio. A steel flange is secured using locking pliers and precisely drilled on a drill press. A centering bushing is placed in the middle of the flange and firmly joined using TIG welding. An angle grinder is used to clean and smooth the welds, ensuring flatness and concentricity. The newly completed hub flange assembly is bolted tightly onto the large sprocket using high-strength bolts. Both sprockets are placed back onto the testing table, with the chain installed to check for synchronous operation. Moving on to the chassis, square steel tubes are assembled into a base rectangle. Each right angle is tacked in place with a TIG welder, creating a rigid, unibody frame foundation. The engineer grinds the welds flat on the corner braces, preparing for the installation of the cross braces. The cross braces are positioned parallel inside the frame, carefully measured with a carpenter's square. Welding the braces in place. This will serve as the main, load-bearing structure for the driveshaft system. Components like the solid steel shaft, bearings, and bearing housings are ready to be pressed together. Using the pressing force of a vise, the bearings are pushed neatly into the housings with absolute precision. 2 drive shaft assemblies are threaded through the bearing units, forming a smooth, rotating, low-friction mechanism. The 2 bearing shaft assemblies are mounted on the cross brace, using light hammer taps to fine-tune their positions. After measuring the parallel distance with a tape measure, they are fully welded to the frame to eliminate play. The 2 sprocket assemblies are installed on the shaft ends, aligning the gear teeth to sit on the same plane. A roller chain is looped over them, and chain pliers are used to secure the master in place. Flipping the chassis over to test the rotation mechanism by hand. It's incredibly smooth, transmitting torque seamlessly. The engineer marks a thick, flat steel bar and drills holes through it to fabricate an auxiliary bracket. This flat bar is welded straight to the rear axle bearing housing, creating a solid mechanical fulcrum for the system. Test fitting the rubber wheel assembly into the U-shaped bracket. To check its range of motion, a piece of thick U-channel steel is carefully marked and cut off amidst the sparks of an angle grinder. The U-channel steel piece is clamped securely and drilled, ready to serve as the mount for the T-hinge assembly. Attaching a large bolt to a round tubular steel shaft, tack welding it to form the core of the pivoting hinge. The hinge core assembly is welded to rectangular steel tubing, forming the joint component of the steering mechanism. Clamping the U-channel steel, the joint, and the threaded shaft together, then tack welding them directly to the drive assembly. The U-joint is centered accurately and welded onto the chassis crossmember. A tape measure is pulled out to check the symmetrical distance on both sides of the steering edge. The engineer continues welding nuts onto both ends of round steel bars to act as tie rods. 4 steering tie rods are bolted, connecting the wheel axle to the central steering lever mechanism. Moving on to the electric hub motor wheel, the core component. Digital calipers precisely measure the shaft diameter. On a load-bearing flat steel bar, the engineer uses a square to mark an angled cut. Specialized steel drill bits pierce the metal surface, creating bolt connection points. The angle grinder cuts decisively along the diagonal line, removing the excess steel extremely fast. The rear subframe is shaped from square steel tubing, tack welded together into a perfect rectangle. The 4 chamfered flat steel bars, just machined, are pressed against the subframe to mark their positions. The engineer fully welds these flat bars with high heat, turning them into a sturdy mounting base. The front and rear frame mounting points are brought together, using a square to align them perfectly vertical. They are locked rigidly together with bolts, positioned right over the clearance of the sprocket system. A piece of round steel is placed vertically, onto the square tubing and tack welded to create the rear wheel fork bracket. The excess square tubing is neatly cut away with a grinder to reveal a secure U-shaped bracket structure. The engineer continues by erecting and welding a triangular tower, using right-angle magnets to set its coordinates. 2 heavy-duty yellow-rimmed pneumatic tires are smoothly slid onto the steering axles on both sides. The electric hub motor wheel is slotted into the U-fork. Then the lock nuts are tightened to prevent the axle from spinning. The engineer installs a leather seat and sits on it to test the load capacity and chassis flex. A tape measure sizes up a piece of steel pipe for the handlebars, welded into a T-shaped angle with the main steering shaft. The age lever assembly for the steering system is welded to the bushing, ready to be assembled onto the vertical shaft body. The steering shaft is inserted through the support hole on the triangular tower, aligned with a set square and welded with a stopper pin to prevent slipping. The steering arm component is tightly bolted to the lower transmission age system. A top-down technical view shows the steering mechanism moving synchronously and smoothly, along with the handlebars. The entire 3-wheeled chassis has taken shape. The steering and transmission mechanisms are fully connected. A thick steel plate bent at a right angle is fitted to the underbody, fastened with self-drilling screws to form a footrest. The semi-finished agricultural electric vehicle has revealed its complete core smart mechanical structure. The next step is fabricating the cargo bed. Square steel tubes are aligned into a trapezoidal frame. The TIG welding torch tack welds it securely at the bevel joint angles. An angle grinder removes the welding slag for a smooth, flat surface. The bottom frame of the cargo bed is then erected, reinforced into a rigid 3-dimensional structure. The 4 side frames of the cargo bed are welded together. A large steel sheet is fitted perfectly inside. The engineer carefully tack welds the sheet edges, creating a tightly sealed and durable material container. The front discharge door is made from a square steel frame, securely welded to withstand pressure. The 4 welding seams are quickly ground smooth, removing burrs to ensure a tight fit when closed. A flat metal sheet is cut to the exact profile, completely welded to the frame to form a finished door. Folding steel hinges are screwed directly into the door frame, using a drill and hex head self-drilling screws. A spring-loaded sliding latch is securely screwed on, keeping the discharge door tightly closed while driving. Checking the smooth operation of the hinges and latch. Every mechanical detail works perfectly. The discharge door is fitted onto the main bed opening, aligning the gaps and screwing the hinges to connect them. A short round steel pipe is welded along the side of the bed to serve as a socket for the material dumping lever. The entire cargo bed assembly is lifted onto the vehicle frame, placed right above the front axle system, using a drill to screw in the undercarriage hinges, turning the bed into a tiltable dump mechanism. 1. Carefully measuring the clearance limits with a tape measure. At the rear undercarriage joint of the cargo bed, a flat steel bar is placed into a bending jig, shaped into an anchor for the side locking mechanism. A round bushing and horizontal shaft are welded to the locking bar, forming a jaw hinge mechanism. The latch pin is securely attached to the undercarriage, locking the bed to the frame when dumping is not required. An eye-catching finishing coat with 3 distinct colors, red, yellow, and blue, has completely covered the frame. Unlocking and tilting the bed manually is very easy due to the calculated center of gravity. A long hand lever made of galvanized steel is inserted into the side bushing and secured with screws. The driver can sit firmly on the vehicle and pull this lever to easily dump the materials. To discharge materials slowly, just unhook the latch and flip the side pin to release the discharge door. Moving on to the electrical phase, the yellow metal battery box is open to install the main power source. 4 lead-acid batteries are placed neatly, using a screwdriver to connect the terminals in series with thick core copper wires. The main power cable and signal control wires are accurately plugged into the electrical circuit system. After wiring is complete, the box cover is closed, and the safety latch is secured to prevent wires from shaking loose. This heavy battery pack is balanced, resting neatly under the operator seat. The mechanical handbrake lever with its sheathed cable is firmly attached to the left handlebar grip. The engineer installs the throttle assembly and switches on the right, while adjusting the tension of the rear brake cable. The forward-reverse switch with a yellow metal casing is clamped tightly to the handlebars with a wing nut. The thick core 3-phase cable from the electric motor is connected directly to the central control circuit, propping up a wooden block to lift the rear wheel off the ground. Testing the throttle, the motor immediately responds with an extremely high RPM. Reverse mode is activated via the switch. The wheel reverses direction smoothly. The electrical system is perfect. Lowering the vehicle to the ground, the driver sits on the seat and gently twists the throttle, gliding around the workshop yard. Moving out to the outdoor practical testing area, the triple tree steering mechanism shows stability and flexibility. The electric motor provides instant torque, helping the vehicle move smoothly with zero noise emissions. For the practical payload challenge, the engineer unloads 10 shovels of crushed stone, completely filling the front cargo space. Even with hundreds of kilograms of stone, the load-bearing steel frame and the motor have more than enough power to pull the vehicle smoothly. The wide pneumatic tires absorb vibrations extremely well. The driver steers the vehicle straight into the dumping area. With a simple pull of the lever, all the stone is dumped out thanks to the undercarriage tilt mechanism. Unlatching the front chain, the tailgate drops down to lie flat to accommodate long, bulky wooden logs. This flexible tailgate design turns the cargo bed into a flat surface, easily carrying materials that exceed the frame's length. The homemade transport vehicle completes the test perfectly, proving the incredible value of applied mechanical creativity.